Okay, can those online hear me? All right, great, thank you. All right, I think we're good to go now. Let's see. Back over here and share my screen. Does anyone have any questions before we get going? No questions? All right. Oh, gotta get my face mask on. So a reminder, the test is on Friday. So the stuff we covered today will be on the exam, or I should say could be on the exam. There'll be a homework assignment associated with it as well. But anything we go over Wednesday will not be, and Wednesday will be a review, okay? So let me restate that. The review part will be on the exam, but any new material, if we get done with the review and start the material, I guess I kind of left myself wide open to say that nothing's going to be on the exam, right?
Yeah, that would have been great. Show up, get an A, and go home.
Yeah, that would be nice. Then I wouldn't be doing my job, so we don't want that. All right. I will also get another classroom for those to make sure we have plenty of room like I did last time. And I believe, as I mentioned before, I will not be here for the exam. And so I'm going to say this multiple times. I'll say it today, and then on Wednesday, I'm going to have to do recruiting on Friday. I'll be at ISU, but I'll just be doing some recruiting. And so there'll be some graduate students. If you have questions on the exam while you're working the exam, just put down any assumptions you make. And I will take that into account if I've made a mistake or wrong grade or anything, but I'm going to try and make sure it's a pretty error-free exam. All right. Okay, with that, let's go ahead and get started here. Bring up the screen here. Okay, there we go. So I want to build on what we've already been working with. So it's just another two new concepts, but they're kind of related and they build on pumps already. So we're going to first start with pumps in parallel. Parallel. All right, what does this mean in parallel? Anyone want to explain that?
One pump's putting pressure, the second one takes it from there and has volume.
Okay, so you're like one step ahead of me because that would be pump in series. Yeah, so.
Two pumps pumping head to the same location from the same location.
Okay, yeah. So in other words, so we're going to be doing pumps in parallel and pumps in series. And pumps in parallel, this used to be a whole lot easier back when civils had to take the electrical engineering course, which we no longer require because we've had to cut back the number of credits, and we talk about electrical circuits, but you may have seen it in physics. I have a pipe coming in to a pump and another pump, and then these two pumps come together and go to my system. This then this is parallel. Okay. So we are, well, I want to ask this question to you guys. What is the obvious thing that we are doing with this versus one pump? When I say the obvious thing, if we're saying that the important things with pumps is the head and the flow rate, okay? Relative to, so this system relative to that system where there's only one pump, which do you think is the most important criteria, the head or the flow rate? Or which one is affected the most? Let me say it that way. So once again, the two most important variables dealing with the pump are the head and the flow rate. if we have pumps in parallel, which one do you think is affected more, the flow rate or the head?
And,
The head? Okay, and why do you say that?
well, because the pipes turn the flow rate more than.
Pipes determine the flow rate. Okay.
Size, where the pump would put more pressure heading to it or more.
Does this pump, does pump A, I'm going to call this A and this is B, does pump A know that pump B exists? Doesn't, does it? Now the system does. The system, when you add the flow to both, the system does. But that therein lies the key. I now have two suppliers to the system. Two suppliers that are trying to give flow to the system. All right? So if they are supplying flow, now I have two people that's trying to bring flow to the system. So I probably did a terrible job of leading you down that path. But the goal I was trying to make here is that parallel pumps add flow. And in a little tiny underneath here, I want to put and head. I can't change, you know. My main goal here is that parallel pumps add flow. So if I'm in a system and I say I need more flow and I don't necessarily want to change out my pump to put in a bigger pump, and there could be reasons why I don't want to do that. Two small pumps offer a lot of flexibility. They offer the ability to turn one pump on when I need it, turn two pumps on when I need more flow, and vice versa, right? So it offers a lot of flexibility. Or turn two pumps on all the time, and if one pump goes out, no big deal. I still have one pump, so I can at least get part of the flow. So there's a little bit of a safety factor there, albeit at a lower flow rate. But there is what's the word? Redundancy. Okay, there is a little bit of redundancy in my system. Unless I absolutely need that higher flow rate, then I may put three pumps in and rotate between them if I always have to use two of them. The pumps in parallel add flow. So if you can kind of burn that in your brain, it's going to help you solve this problem. Because our system curve does not change. After this right here, the system knows that there's flow coming to it, but it doesn't know that it's supplied by two pumps. It doesn't know that it's supplied by three pumps. It just knows that there's flow coming to it, okay? So the system curve does not change. The operating point changes. Okay. So the process, we add pump curves horizontally. More flow. So this is the concept, and I'm trying to tell you that pumps in parallel add flow. So you should say to yourself, oh, I'm going to add flow, so I'm going to go out on the x-axis. Okay? And we use then the principle of superposition. You guys familiar with the principle of superposition? Should have seen it in probably structural analysis. Sometimes in hydrology when you're going with groundwater. Other places in engineering, the principle of superposition means that we just add them together, right? So what this tells us is that if I have pump, okay, let me finish this out here. Say given two identical pumps, two pumps that are the same model, same motors, everything. So given two identical pumps, I then can take the one pump curve, so pump curve A, and pump curve B. All right, I'm going to try and draw them the same the best that I can. And now when I add those two together, then I'm going to get pump curve A plus B. I'm going to use a little line here to represent the head. I didn't draw those too well, but that represents then the shutoff head. So I'm going to draw pump curve A, and then I'm going to come in and add pump curve B. And that was terrible. I should have used my erasable pen. It should be up to here. All right. Here's the concept. If I have this distance right here as L, L1A, and over here at the same height, I have L2A. And what's the relationship between L1A and L2A? They're the same, okay. So now I'm just going to come over here to my combined pump curve. I'm going to put in L1A, and I'm going to come in and put in L2A. And for similar pumps, same size and everything, those distances are going to be the same. And then I can also come down here to the bottom and put in L2A and L2A, sorry. Sorry. The first one should be L2B, L1B, sorry. Monday, I'm going to blame it on. L1B.
Oh, you've got those labeled as curve A and curve B. So wouldn't it be L2A?
2A, thank you, yeah. Good thing someone's watching out for me. And over here, this is going to be L2B, right? And up on the top, that should have been L2B, L1B. Ah, how about I just go home and go to bed? All right, there we go. L1A, L1B. And then L2A and L2B. And I can put those in over here. So L2B and L2A and L2B. Man, that was a terrible notation system there. I just should have called those A, B, C, and D. Would have been a whole lot easier, right? L2B. Noting then that L1A is equal to L1B and L2A is equal to L2B. Okay? Now, my little graph up here is pretty messed up, so I'm going to draw a new combined graph down here on the bottom. Make this bigger. All right, so if this is pump 1, just using my fingers here to measure approximate distance between each of those. So now I can draw my second pump curve. Of course, it comes back to the same spot because if you add 0 plus 0, you get the same value. Okay? So this is one pump. This is two pumps. All right. Now, if I go ahead and put my system curve on, I'm going to draw a random system curve. Call this my system curve. And hopefully that you can see that by adding another pump, my flow and my head increase, but it's mostly my flow that increases. Okay. Let me bring my red pen today. But my operating point, this then here right here is going to be one pump. That pen's dead. One pump operating. And right here is going to be two pumps operating. So if I turn one pump on, it's going to operate right there. That's where the pump curve intersects the system curve. If I turn two pumps on, it's going to operate over here. Okay. Does this mean that the first pump is putting in this flow rate down here, and then the second one is adding to it? Does one pump know that the other one exists? It does not. And which pump would be putting in more? And if they're the same pumps, wouldn't you expect them to put the same in? Right? That makes sense, right? So notice if I come back horizontally to one pump curve, now these two are essentially the same. So Q and Q, both of these pumps, since they're the same pumps, are going to be put in the same flow rate because they're pumping against this head. Since they're pumping against this head, each pump is putting in half of the flow. Because we're putting more water in our system, the friction losses go up. Our delta Z does not change. How high we're lifting the fluid doesn't change, but because we're pumping more water through our system, the friction loss goes up. That's why our pump curve goes up. And that's why we don't double the flow. We don't double the flow from the first pump, but we do increase the flow. We don't double the flow because the friction losses go up. But each pump is, since they're the identical pumps, they put in the same rate. Questions on this? Feel comfortable with that? Aaron, how are we doing? Something not quite lining up?
No, I'm just trying to make sure it makes sense to me.
Yeah, well, I get that.
So when we add those together, when we, on a pump curve, we would go horizontally back across to get the flow rate for each one. It should be the same.
At a given head, at any given head over here, the distance from our y-axis to the pump curve should be the same distance as pump curve 1 to pump curve 2. Because that's the principle of superposition, add them
As
together.
long as they're the same pump.
As long as they're the same, that's the key, as long as they're the same. And we'll look at dissimilar pumps in probably on Wednesday, but as long as they're the same. Okay? All right, now if I want to evaluate the performance of a pump, realizing that each pump doesn't know that the other one's there, what head are they operating at? This head right there, right? And this flow rate. So I would bring everything back to this point to evaluate my pump. It's efficiency and the net positive suction head. So the key point here is always bring performance back to single pump curve. Always bring the performance back to a single pump curve. And because the pumps are operating at this head right here, we know that the flow then is going to be half for each pump. of the system flow. The system, if the system has 100 gallons per minute, each pump is going to provide 50 because they're the same. Okay, and they pump against this head. That's all that pump knows. It knows that I have to pump water against this head. It doesn't know what else is coming into the pipeline down system, but it knows if I have to pump it at this head, this is where I'm going to operate at. This is my efficiency. This is my net positive suction head. Okay?
Can you explain that again? So like, where is that relevant when you're doing calculation that you would use that operating point?
So this operating point is the operating point for a single pump in a system with two identical pumps in parallel. Okay? It's the operating point for a single pump with two pumps in parallel. Now, if I had three pumps in parallel, but my system curve went through and I brought the head back there as well, that would still be the operating point. So this is the required head for my system. In order to get flow to go through the system, I look at where the system curve and the pump curves intersect. I bring the head back, and that's where one pump is operating at. It's operating at that head, and that's all it knows. I have to push water against this head. How much can I push? I can push this flow rate right there. All right.
So what's that circle, the little circle you drew, like where the two,
Right here?
yeah.
Okay. This is for a pump, a single pump operating by itself. Okay.
But then that one's for the single pump parallel with that.
Yes. So this is one pump, and it kind of, the pen didn't mark it very well up there, one pump. And this one up here is two pumps operating. But when the two pumps are operating, we have to go back along the head curve, along the head to see where the single pump is operating at, because that's what it's pushing against is that head.
That would be the find the flow.
To find the flow of a single pump, to find the efficiency of a single pump, and to find the net positive suction head of a single pump. Okay. All right.
So we're finding.
Hey, Dr. Savage.
Yes.
So this only works with the two pumps being the same. Otherwise, you would have to go back and look at both of the pump curves individually.
Correct. Yeah, if we have dissimilar pumps, which we will talk about, like I say, after we've gone through the basics here, you would have to go back and look at each pump with the same head that the system is operating at. Okay, and that's the key part, is the same head. The pump only knows how much head it's pushing up against. Laura?
So if you are looking at the graph with two pumps, and then you go over, find that head, and it's the same as for just one pump, well, it's higher, but then do you use the flow rate that you find from one pump or two?
You use the flow rate from two pumps, but you have to split it in half, which takes you back to here. One pump can push this much, but when you throw another pump on there, because the head, the friction loss increases, it can't double the flow. It doesn't double the flow because of the increase in head right here, this delta H. Okay, so you come back across here to find this operating point right there.
Oh, gotcha. So you'd say the first pump uses a different flow than the second one? Or do you use the same flow?
The first, if they're operating together, they have the same flow rate. If one's operating by itself, we turn one pump off and only operate. So if we only turn on one pump, we turn on one pump, our system comes to equilibrium, it's going to be pumping this right here. Then we throw the other pump on, and it's going to go out to here, but the amount of flow coming from pump one reduces back to here because it has to increase the head that it's pushing against.
Gotcha.
Okay. Those online, any other questions that you may have? Okay. let's talk about pumps in series. Okay, pumps in series is where you have a line come in to a pump, which then supplies another pump. And I'm going to put 2 in there, but you could have more. Okay, and a little caveat here is always use the same size. Now with parallel, we don't have to use the same size, but in series, can you imagine pump number 1 pumping 100 gallons per minute and pump number 2 only being able to pump 50?
Would it be a restriction?
Yeah, it would be a restriction. And if the reverse is even worse, if pump number 1 can only pump 50 and pump number 2 can do 100, now you can't supply enough flow. You're going to create low pressures and you're going to cavitate. So, I mean, if you really get into pumps, they may change them like 1 or 2% due to some losses, but you want them essentially the same. Okay. So this should be a hint. The flow rate's the same. What's the advantage of adding a second pump? Adds additional head. Adds no additional flow, it adds additional head. So pumps in series add additional head. Okay. Flow stays the same. Now this is pretty common. A lot of times they'll put pumps together, the pump themselves, like the pump impeller. And one pump impeller will feed into another pump impeller, which will feed into another pump impeller. They call them stages or bells. So if I'm 600 feet down trying to get water out of a well, trying to design a pump with a single impeller that can pump 600 feet is pretty tough because of the tolerances. The amount of tolerances you have to have so the water doesn't slide back around the impeller at that kind of a pressure is very, very tight, so it costs a lot of money. But it's not so hard to put 6 pumps that do 100 each together, and you can even put them on the same shaft and use a single motor to drive them. But one impeller adds 100 feet, the next impeller adds 100 feet, the next 100, next 100, next 100, and so on up to 600 feet. Okay? So each pump's only adding a small amount, but they are cumulative, they add on each other. All right? So now, if I'm trying to take this pump curve and add it with this pump curve in series, since we are adding flow, and it is the principle of superposition, whoops, that's a terrible pump curve. We are going to go vertically and add them up. So pump A, pump B, over here we have A, we have B. Let me do the same thing. Let me draw a bigger picture. So here we have flow. I should have notated my axes. So here I have a single pump curve, and I want to add it in series. So I look at this, I have H naught going up to the top right there, right? And so when I add one more pump, I'm going to come up another distance of H naught. And that's going to be 1 point. Then I'm going to come in and find a point down here. And we'll call this, we're going to call that H sub A, and I'm going to take that and physically add it on up there. And here. You get the concept that this right here, h sub b, so we know that h sub a equals h sub b. Those are the same, right? And then I can do the same thing down here. This distance down here, add that up there. And so if this is h sub c and h sub d, h sub c equals h sub d. Those are physical lengths. So now that I've got my 3 points, I can redraw my pump curve. So whereas the bottom one is just pump A, the top one is A plus A, or A plus B, however you want to look at that. So when you're graphically doing this, remember we said you need 3 points to do a curve. So I just grab 3 random points, measure, add it on top. So it's just like parallel. Parallel, I take a horizontal line and add it out this way because I'm adding flow. In series, I'm adding head, so I take a vertical line and add it up. Take 3 points, draw my new curve in. Okay? Now, if I took my system curve, whereas I would operate right here at the intersection for one pump. So this is, and my pens, I get new pens here. This is one pump. And where the system curve and the 2 pump curves interact, that is, this is 2 pumps. Okay. So, following the concept that we use for parallel curves, if I want to find the performance of one pump, what do I do?
Straight down from the 2 pumps, so you meet the first pump line.
Excellent. I find out at what head is one pump operating at. And as Aaron noted, I'm going to come straight down and note that this point right here, that's where the pump is, where the single pump is going to operate in a 2 series pump configuration. Let me say that again. This little spot right there that I've drawn, tried to put an X through, haven't done, there we go. X is getting pretty ugly, but that little X point right there, that's the location where a single pump in a 2 pump series configuration will operate. And it's going to be half the head of the 2 pump configuration, which makes sense. Pumps in parallel are half the flow, pumps in series are half the head. One pump provides half the head, the other pump provides half the head. And just like the pump in parallel, always go back to a single pump curve to evaluate the performance. Always go back to a single pump. Now, if I had some method of turning only one pump on, let's say my pumps were separated by a small piece of pipe, and I had like a valve where I could redirect the flow. So if I only needed this much flow rate and this much head, I'd just turn on one pump. And then if I needed additional flow and head, I get a little bit of flow out of this, right, by adding another pump on there. I would then turn on the second pump and it would increase the head and it would increase the flow slightly from only having one pump. Because now I have 2 pumps that are trying to pump the flow. I'm splitting the head between them, reducing the total head that each pump has to pump against that system curve.
So
Lauren.
for the series, since it's adding head, that's why we go vertically
Yes.
down.
But then for parallels, you're just adding flow, we go horizontal.
Yes. And, or you could ask the question, at what head is this pump operating at? And that answers both questions.
Okay.
At what head is this pump operating at? And for parallel, you have to go horizontally to bring the head back to a single curve. And for series, you have to come vertically to bring it back to the head for a single pump curve. But it's all based on the head. Get the correct head, and then the flow rate will fall out. Okay. Samantha, was that a question or no? Okay. All right. Those online, any questions?
So depending on your system curve and the steepness of the system curve, if you're in a situation where you believe you need multiple pumps, if you had a relatively flat system curve, you gain more benefit by adding pumps in parallel. And if you had a very vertical or very steep system curve, you gain more benefit by adding them in series.
Correct. That would be a valid statement. Laura?
Do all the pipes have to be the same size, like in diameter and length?
For pumps in, do they have to be? No, but if the pumps are the same, it would be a good idea. I mean, would it still perform? In series, I think you'd have problems. But I would also note once again that most of the pumps in series are connected at the pump itself. Just give you just a really quick idea here. So this one right here, inside of there's going to be multiple pumps in there. That doesn't show it very well. Let's do pump series. It shows curves. Let's do series pumps. Pump valves. How come it's not showing me yet? I just want pump valves. And this is kind of what it is, but that's not showing it very well either. Okay, this picture here. So you can see this is a vertical turbine pump. And so the motor is up here, okay, and you have a long shaft that goes down, and you see that there's this is the inlet down here, the intake, and then you have this bowl right here, and then you have another bowl right there, another bowl right there, okay? So this is one pump, this is two pumps, this is three pumps, and they're all powered by the same motor. So the first impeller is here that feeds to the second impeller, which feeds to the third impeller. And that's the majority of what pumps in series are. They come pre-manufactured already in series. Now that doesn't mean you can't put them in series, and there are times when we do. You know, if we have to lift the water up over a hill, we put an inline pump, and then we say, oh, we need a little more flow. Well, we're going to put another inline pump behind it and use the same size piping to get it to go to add additional head to our flow. But majority of them are like this, and although they may not look like that, you know, maybe I'll see if I can bring some impellers from my office. I have a couple over there and kind of show you what they look like. Okay. Other questions? Okay, let's start on an example. I don't know how far we're going to get on this. For those online, I did post it to Moodle. Was a little late, but it is there. Okay, so I have this system here. We want to evaluate the system curve for the system shown below. Determine what pumps or pumps. It should be pump or pumps. It should be pump or pumps. We'll do the best job and then show you work on the pump curve on the next
It's not
page.
showing it, though.
Oh. That's weird. Don't know why that was, but here we go. Okay. So we've got a short little section going up to our pump. And then we've got the line going up to our other reservoir up here. And we want to find then what is the correct pump that we want to stick in there to get this system to work. And our goal is 500 to 600 gallons per minute. Okay. Now, we could work through this and note that I did say neglect the minor losses, so we don't have to worry about the check valve. We don't have to worry about entrance or exit losses. And if you work through this, you should find for your system curve that the total dynamic head is equal to 110 feet plus 17.26 times Q squared. Yeah, and Q is given in units of cubic feet per second. Okay. And so C is equal to 17.26. So you're familiar with that, right? Let's just check here. We're going from an elevation of 0 up to an elevation of 110. Delta V is then 110. So that makes sense, all right? And then once again, if you check friction loss in both of those pipes, that's what you're going to get. So now I can go ahead and take that and put that on the system curve. Sorry, on the pump curve. So I come over to my pump curve. Now let me bring my pump curve over here. I want to put this on the pump curve. And so my first point is going to be right here at 110 when there's 0 flow. Okay. And I look at that and I say, that to me doesn't look like I'm going to get much flow because my pump curve, no matter how flat it is, I mean, it'd have to be really, really flat. I know it's not going to be that flat for me to get 500 gallons per minute. It's really not going to make it. Okay. So my gut feel is that I'm going to need pumps in series to add more head to get this to work. Okay. And I didn't need to define then, well, first off, let's get the system curve on there, and this will make that more obvious. So I first need to build my system curve. So at least 3 points for my system curve, right? So I'm going to come over here and I'm going to say Q in gallons per minute. And that's going to equate to Q in cubic feet per second. And then I can go ahead and calculate what the H is for the TDH, total dynamic head, in terms of feet that I need to add to my system. So if I have 0 gallons per minute, that's going to be 0 CFS. That's going to be 110 feet as expected by sticking 0 into my equation. Okay. Now I'm going to pick 400 gallons per minute. 400 gallons per minute is going to be 0.89 cubic feet per second. I plug 0.8.9 into my equation, and my head then, excuse me, is going to be 124 feet. And now I'm going to pick 800. Okay, 800 is going to be 1.78 cubic feet per second. And when I plug that in my equation, that's going to tell me 165 feet. All right, come back to my pump curve over here. Okay, 0, 110, it's pretty simple. All right, 400, at 400 gallons per minute, I need 124 feet, so I'm going to come straight up here. There's 120, there's 130, I'm going to split that difference, and here is 124. 24. And then I'm gonna go out to 800, and 800 is 165. So I'm gonna come up here, and then here's 160. The next one would be 180, so 170, split that difference, and it's gonna be right down there. So now I have my system curve. I can draw my system curve on there. Best I can. That's how my system is going to operate. Okay. Now I know that for the, if I was operating with just pump A, I'd have about 350 gallons per minute. Not going to cut it. Okay. If I was operating with B, I would get maybe somewhere in the order of 150 gallons per minute. If I had impeller C, I would get no flow. Or it actually run backwards, except I have a check valve in the system. I get no flow in the system. All right. But I want 500 gallons per minute, 500 to 600. So I know I need to add pumps in series. Now I could plot A, B, and C on here. In the interest of time, I'm going to say let's go ahead and use C. So we want to use C plus C. Okay. So I'm going to come over here with C, and I'm going to say that I have about 90, I don't know, 90, 93 shut-off head, 93 feet ahead. So that's going to take me up to 186. So this is 180, and this is 200 up here. 180, 186 is going to be somewhere right around in there. That's my little point. Okay, I'm going to go ahead and pick right around 400 again. But now, to make my life easy, I'm going to pick where it crosses the horizontal axis here. So I'm going to say vertically up here, I'm going to add 80 because that's where that C line crosses the 80 feet ahead. And so I'm going to come vertically up, and 80 is going to be 160. So I'm going to put in another point right there. I'm going to double it. So right here, you see I'm working on the C line again. So whereas this is 80, I'm up to 160. Okay. And then one more point. It doesn't quite go to 800, so I'm going to pick 700. And at 700 gallons per minute, I'm about at 50 feet ahead. So I'm going to come up to 100. And put my point right there. And now I have my three curves, and I can draw my combined pump curve of that system. Okay, we're out of time here, but really quickly, now I know that my pump curve and my two pumps in parallel, C plus C, and my system curve intersect right there. So now I'm going to come straight down and find where that intersects with a single pump, C plus C, and that's where the single pump operates right there. Single operation. Not a single pump by itself, but a single pump in series. And now I can get all the information about how much head one pump adds, how much flow one pump adds, what is the net positive suction head. I can get all that information from one pump curve, and I can go back and solve those other questions of what is the pump horsepower, what is the brake horsepower, what is the total power, how do I calculate the energy. You've done all those already. Okay. So really quickly, if you want the answers, B, H to P is approximately 135 feet. Q is approximately 560 feet, or I'm sorry, gallons per minute. The efficiency of the pump is approximately 82%. Net positive suction head required is 12 feet. And then I get water horsepower equal to 19.1, brake horsepower equal to 23.2. And then the total power, I didn't calculate the total power. I did that as part of the, I did that as a part of the total power cost. Oh, I guess I did. The total horsepower then is 22. Oh, that's not right. Oh, yeah, it is 22.24 kilowatts. I changed the units. And the total cost of operating this is $3,044 per year. Sure, sorry. So those are the answers to that. I appreciate your patience. We're out of time. But that gives you an idea how to go through an entire problem like this. Remember, parallel, add flows in, add the pumps in flow rate, the horsepower, add them series, add them vertically. I'll put 2 homework problems for you guys to solve. Your experience with this. Have a great day. We'll see you on Wednesday.